Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely, and in this video we will talk about triangulations, which are the subject of the start of chapter 3. Here's a definition of what a triangulation is. We're given a d-dimensional polytope P, and a triangulation is a finite collection of simplices of the same dimension. So let me remind you what a d-dimensional simplex is. This is a d-dimensional polytope with a minimal number of vertices, namely d plus 1. And then for this collection T to be a triangulation, I need to have two properties. Number one, the union is all of P, the given polytope. And number two, any two simplices in the triangulation meet in a common face. Let me illustrate this definition by giving you both examples and non-examples of triangulations of this hexagon. So I think of this as my given polytope P. P is two-dimensional, so I would like to write this as a union of triangles. So maybe I'll start here with a triangle, and here with a triangle. This, what I have so far, is not a triangulation yet, because the middle piece is not a triangle, it's a quadrilateral. We can continue and maybe do something like this. So now I see P as the union of 5 triangles, but I'd like you to realize that this is not a triangulation, because I have a triangle over here, and if I intersect that with this triangle over here, this intersection will be this line segment over here, which is a face of the second triangle, but not of the first. We can fix this by subdividing this triangle over here into two. And this is now indeed a triangulation of my given hexagon. This is a triangulation where I introduced new vertices. So here I'm not just using the given 6 vertices of the hexagon in my triangulation. There are other triangulations, for example, this one. This is a triangulation of P, and it uses only the original 6 given vertices of P. And the main theorem that we're after in section 3.1 is that something like this is always possible. Every polytope, any dimension, can be triangulated, and in fact it can be triangulated using only the original vertices, only the vertices of P. This seems to be intuitively clear, but this theorem needs a proof, and what we're doing in section 3.1, giving you a quite constructive proof. My goal in this video is to give you sort of an overview of where this proof comes from. And to do that, I need to talk about simplicial polytopes. So what is this? So polytope P is simplicial if all proper faces of P, so what that means is all faces other than P itself and the empty set, are simplices. So the faces come in different dimensions, and so what we're saying is they're all simplices of different dimensions. You might realize I can be cheaper in my definition and simply demand that all facets, So these are the codimension 1 faces are simplices, because once a facet is a simplex, all faces of that simplex is again going to be a simplex, and so this is good enough for my definition. In this picture, you can see the cross polytope in 3 dimensions. It's the classic example of a simplicial polytope. So you see one of the facets here is a triangle, and there's 8 more. And so you can see all the facets, and therefore all the faces here are simplices. Let me make 2 remarks. So number 1, if I pick the vertices of P, I'm defining a polytope as a convex hull of some points. If I pick those randomly, then I claim P will be simplicial. A quick reason for that is that any hyperplane in some, let's say, d-dimensional space is determined by d points. So for example, a line, which is a hyperplane in R2, is determined by 2 points, unless the 2 points coincide. And a plane in R3 is determined by 3 points. Again, I have to choose them smartly. The 3 points should not be collinear, but if they're not, then those 3 points will determine a plane. So now, if I pick vertices of P, and I think of P as a d-dimensional polytope now, at random, that means no d+1 of them will live in a hyperplane. And in particular, that means any facet-defining hyperplane will have at most d points. But that means the facet is a simplex. I have d points giving you a d-1 dimensional polytope. That's by definition a simplex. There's variants of this. I actually don't have to pick all the coordinates of my vertices at random. I could, for example, just pick the dth coordinate and so now I really think of P as living in R to the D. If I just pick one coordinate at random, I claim exactly the same reason will give me that P is simplicial. And we will use this fact. So this is my second comment about simplicial polytopes. What I will now do, I will project all the points that you sort of see in this octagon from below. I will project this to a plane, and so in this plane I will see a square of sorts. But now I will also project the facets that you see from below, and I will carry this information with me. And so what this will give you is a triangulation of this square. And I hope you can see that this triangulation comes directly from the simplicial structure of the polytope 1 dimension higher. So the idea that we're now going to pursue is to reverse this process. I will start with a polytope. I will move up 1 dimension higher, construct a simplicial polytope in such a way that if I project those facets, those faces that you see from below, they will induce a triangulation of my original polytope. So let me show you what happens with the hexagon from before. So what we have is polytope P. Let's say it's given as the convex hull of in this case 6 vertices, and it lives in R2. And what I'm going to do is I'm going to construct a polytope Q by giving each of the vertices a third coordinate. And I'm thinking of this as a height. And this third coordinate lifts my resulting polytope into 3 dimensions. And I want to do that in such a way that Q will be simplicial, and that the facets of Q that are visible from below project to a triangulation of P. You realize by now that there are a bunch of terms that I'm giving you an intuitive definition of, but I'm not defining them rigorously. One of those terms is visible from below. You can think about how to do this mathematically, but at any rate, you will see a rigorous definition in the book. Okay, let me do the following construction. So what I'm going to do is I will leave these 2 vertices of my hexagon where they are. I'm not giving them height 0 if you want. And I will lift these 2 vertices to some height in such a way that this will produce, if you think about sort of folding a piece of paper, this will produce a crease here. Now you can see I can do this even further. I can lift this vertex further up, which will produce another crease here. I can do the same thing on the other side. So there's 2 more vertices that I sort of haven't touched. I take this vertex here on the right and lift it again to some positive height, I will produce another crease here. What you should imagine here is some sort of partial folding of my hexagon, where the 3 orange vertices get some positive height function, and the remaining 3 green vertices stay where they are. And then again, I need to think of the height of this vertex on the left sort of higher than its neighbor up on top. And so I get a partial folding of my hexagon that induces the triangulation that I'm after. And mathematically, the way I do this is I lift my vertices, I take the convex hull, so this will now be a 3-dimensional polytope, and then I look at that 3-dimensional polytope from below, and because this higher dimensional polytope is simplicial, if I project that now back down, I get a triangulation. There's nothing special about 2 dimensions here. You can do the same construction in any dimension. You will go 1 dimension higher by introducing heights. You need to define what it means to be visible from below, what the facets are that are visible from below. They're called lower facets. And then you need to define sort of the correct projection function to map back to your original polytope and then see the induced triangulation. Any triangulation that's obtained in this way is called regular, so that's the word that you see here on top. Not all triangulations are regular. This is another instance where 2 dimensions are special. So in 2 dimensions, and you can think about it why this is true, any triangulation of a polygon that doesn't use any new vertices will be regular, but this is far from true in general dimension. I hope you're convinced that regular triangulations always exist, And this gives us the theorem that we were after. That give me any polytope, you will have a triangulation. There's a lot more we could say about triangulations. In fact, we could come up with a whole course studying triangulations. I recommend this book to you by Jesus de Loera, Jörg Rambau, and Paco Santos. It's a beautiful book about all sorts of theorems and algorithms for triangulations of polyhedra and of more general sort of point sets.